Hi, coming to you with the YouTube webcam, which is why perhaps my lips don't match my voice. But I took a look at the problem set due for Monday, and I wanted to give you a couple of heads up, those of you who care to look. Uh, Let me work backwards from recollection here and let you know that you really very often you have to break things up into two free body diagrams. So you might have a rock tipping on one thing, and that means you're going to have a fulcrum where it's touching one place and weight is acting down and something else acts back up. And then what you know is you have equal and opposite reactions, and so you might have another fulcrum problem there. That's one thing to remember. Working forward through that problem set, and I'll look at it one more time, is when you're looking at concurrent force problems, basically, if it's a static problem, then the sum of the forces equals 0. And so you sketch out all of your knowns and unknowns emanating from the point of concurrency. And that's usually, if you have a bunch of cables tied to the end of one point, that place that the cables are anchored to is the point of concurrency. You also, sometimes you're given based on some description there. Maybe you don't know what the sum of the forces is per se, but you might know that the sum of the forces is vertical or the sum of the forces is horizontal based on some sort of general description. So I think there's a problem there where you have to assume that the sum of the forces of the wires is actually straight vertical and then realize that the pole is pushing back up. These things are very often easily done by graphics, by sliding things tip to tail and starting with this if you're going to do it graphically. Basically, if you have two unknowns and two unknown magnitudes and two known directions in your kind of unknowns, what you do is you add up all the vectors that are known, and then you decide to go back to home via one of the other vectors. So you have basically two known directions for your unknown vectors, if you would. And you basically figure out that's the way you're going to walk home back to 0. And now you consider yourself standing out on the end of that, all of the known vectors, and you have to walk back to that line via a direction that's the same as the other unknown direction. So there's problems like that. There are also problems where you know perhaps the magnitude of the vector but not its direction, and you get those by swinging arcs. Realistically, you can do all of these by writing sum of the forces in the x and sum of the forces in the y and solving simultaneous equations. But those are some of the tips and hints that I have for you. Those problems are relatively basic, especially the first 4. If you remember the facts and sketch things out and realize that very often you might not know what the sum of the forces are, but you might know that the sum of the forces of a set of cables might be in the x direction or the y direction. In other words, they don't have a component going in the other direction. So I'm going to go ahead and put this out. It's about 4 minutes here. We will look tomorrow in class. I'll have you take a look at these and get a general hint and go from there. Remember to review what we did in class today out on the web in some other format. That fact that in a set of parallel non-concurrent forces, that you add up the forces tip to tail, and then the line of action is a line of action that causes the same moment about any point as the sum of those forces. So we'll go and hit that, and we'll see what this looks like when you record directly via webcam to YouTube.